Good morning, everybody. Welcome to the Planetary Science Sample Seminar Series. We are delighted to have you guys here today with us. We have a special guest with us today. Prajkta is going to be giving us a talk on the distribution of the short-lived radionuclide niobium in the early solar system. And so a little bit about Prajkta. Her research focuses on the study of chemical, microstructural, and isotopic characteristics of meteorites. She analyzes calcium aluminum-rich inclusions, or CAIs, to decipher chronology of early solar system events, observes the recorded nucleosynthetic anomalies in them, and studies their microstructural characteristics to determine the mechanisms of CII formation. She also analyzes Martian meteorites for their hydrogen isotopic composition to understand the evolution of Martian water reservoirs. So, Prajkta, please take it away. We are so excited to have you with us.
Thank you. So I just have one screen in front of me. So if you have any questions, if anyone has any questions, please stop me and speak up, and I'll be happy to answer them during the presentation. Thank you very much for that introduction. So today I'm going to be talking about the distribution of short-lived radionuclide 92 niobium. And I would like to thank all my collaborators. A majority of this work was done at the Lawrence Livermore National Laboratory with Greg Brenica and Jan Render. But I also have a bunch of other folks here listed who have contributed to the discussion and interpretation of the data at various levels. So thank you for that. All right, let's see. So I'm going to start with this quote by Carl Sagan: "The cosmos is within us and we are made of star stuff. We are a way for the universe to know itself." So this part about we are made of star stuff is actually literally true. Here is a periodic table with all the elements and their origin or the sources of these elements. Our sun is a second generation star. It's still in a state where it's in its core, it's converting hydrogen to helium. And all the other elements that are present in our solar system were generated, formed in other circumstellar environments, and then they survived their journey and then they were contributing to our own solar system. So there is a lot of evidence for these surviving circumstellar materials in primitive meteorites. One of the first evidence is actual physical form of stardust, which are these pre-solar grains. And here are some examples of those. Here is a silicon carbide and graphite grain from different primitive meteorites. Now, these primitive meteorites are basically sedimentary rocks that collect different dust from the early solar system, and they haven't undergone any thermal processing, so most of the material survives. And here, if you look at the size of these, they are few microns to few hundred nanometers in size. So they're really tiny. But how can we tell that they're pre-solar or they're coming from other stellar systems is based on their isotopic composition. So here is an example of oxygen isotopes. Oxygen has 3 isotopes, 16, 17, and 18. So here on y-axis, you have 17 to 16O ratio and 18O to 16O ratio. And as you can see, the solar system falls at the intersection of these dotted lines over here. And both the scales are here logarithmic. So the variations that you see in these oxygen isotopes are actually huge. No physical or chemical process in our solar system can actually form these kind of variations. However, various stellar nucleosynthetic models can explain these variations that have been seen in these pre-solar grains. And that's how we think that these are pre-solar in nature. So this is just one example of oxygen isotopes. There are several other isotopic systems that have been analyzed in these pre-solar grains. It is another example of titanium isotopes, which also shows significant amount of spread. The next stage of isotopic heterogeneity that suggests that there are some pre-solar components in the early solar system are these calcium aluminum rich inclusions. They are millimeter to centimeter sized objects that are again preserved in primitive meteorites. So here is an example of such primitive carbonaceous chondrite ianthe, which is a CV3 meteorite. And here is a picture of a CAI. They are larger than the pre-solar grains, but the anomalies that you find in these CAIs are much smaller at their scale. So there are several isotopic systems again that have been analyzed that these CAIs have been analyzed for, and you can see variations in epsilon units or parts per 10,000 scale. So the next step is the bulk meteors. Oh, another thing about these CAIs is that we think that they are first form solids in our solar system. They are first form dated solids in our solar system, and they show presence of various short-lived radionuclides. For example, 26 aluminum, or another example here is 182 tungsten. Short-lived radionuclides are radioactive isotopes that decay to their daughter products with a half-life which is about less than 100 million years. So most of it has been decayed by now, but we do see evidence of those in these isochrons as we analyze these CAIs and other meteoritic materials. All right, someone is typing very loudly. Could I please request you to mute your microphone? Thank you. So the next type of isotopic anomalies, or the evidence of these pre-solar components surviving in our solar system, is seen in bulk meteorites. Here is a very classic example of such isotopic anomalies that suggest that astromaterials or meteoritic materials that we have in our collection essentially fall into different groups. So here you have oxygen isotopes on y-axis and chromium isotopes on x-axis that show these two distinct groups that have been defined as carbonaceous and non-carbonaceous reservoirs in the early solar system. Now, again, the scale of these anomalies, as you can see, is much smaller. So it's parts per million units, so mu unit. So here is another example of such isotopic anomalies in stable 96 zirconium isotope that also shows these heterogeneities, but and two distinct isotopic reservoirs. So these are just two examples of these three different isotopic systems, but there are several other isotopic systems in which we see this distinct difference and the two different reservoirs in the bulk meteoritic materials. So again, to summarize, what I just mentioned is that the scales of isotopic heterogeneity in the early solar system are different. The materials that survive are different. So as you go from smallest materials, which are pre-solar grains that are actually survived materials from other circumstellar environment that show huge variations in their isotopic composition. Here is an example of titanium isotope system here on this plot. So pre-solar grains show a huge variation. Then you have CAIs and maybe contour components, which are centimeter to millimeter sized objects that form very early in our solar system. And they survive any further processing, and they show a larger or smaller scale variations compared to the pre-solar grains, but still significant amount of variations. And then the next scale is the bulk asteroidal material. So here I have an example of asteroid Vesta, which has a diameter of about 500 kilometers. And this is one of the larger asteroids in our solar system that has survived. But the isotopic variations that you see in these bulk large meteoritic materials are much smaller in scale. So there is a different levels of isotopic heterogeneity that have survived in different materials in our early solar system. So I talked about isotopic anomalies. So let's try and define what they are. So there are three different types of isotopic variations that we can see in in the materials. The first one is mass-dependent isotopic variation. So here is an example of oxygen isotopic plot again. Here 17 on y-axis, you have delta 17O, which is the ratio of 17 to 16. And on the x-axis, you have a ratio of 18 to 16. So the mass difference between 18 to 16 is 2, and on the y-axis, it's 1. So any physical or chemical process that fractionates isotopes or causes these mass-dependent variations are going to fall on this slope 1 line. So everything that's on Earth, different materials, they fall on this line. And this is defined as a mass-dependent variation, which is due to chemical and physical processes that happen in these materials. The second type of isotopic variations are mass-independent variations. So here is a strontium isotopic plot that I've stolen from one of Greg's papers. Here what you have is materials that have been correct. This is the original isotopic composition that is seen in green. And then once you anchor it to one isotopic system, you can get rid of all the mass dependent variations. And in that case, what the anomalies that still survive are going to be mass dependent variations. They are stable isotopic variations, and in meteoritic materials, they are called as nucleosynthetic anomalies. And as they are stable isotopic materials, isotopic variations, they have infinite shelf life, meaning the only processes that can change them are physical and chemical processes, so like mixing or sorting of different grains, etc., that can that can affect these variations. The third type of variation is radioactive decay. So here is an example of a short-lived radioactive system, 26 aluminum, 26 magnesium, where 26 aluminum, being the parent product, decays to 26 magnesium and changes the isotopic composition of magnesium isotopes. Since these variations have a half-life associated with them, they are very time sensitive. This radioactive decay and the variations are time sensitive, and they can be used, in some cases, they can be used as chronometers to date various events. So let's talk about short-lived radionuclides. How do they work, and how can you use them to date different materials? So here is an example of a short-lived radioactive system, 26 aluminum. 26 aluminum has a half-life of about 0.7 million years. So all of it that existed at the beginning of the solar system has been completely decayed. But we use 27 aluminum, which is a stable isotope, the only stable isotope of aluminum, as a proxy for 26 aluminum. So here on x-axis, you have a 27 aluminum to 24 magnesium stable isotopic ratio. And on the y-axis, you have a ratio of 26 magnesium, which is the daughter product of 26 aluminum to 24 magnesium. So at time 0, when you have a chemical fractionation, and if you're forming an object like, say, a calcium aluminum rich inclusion or a differentiated meteorite, is going to chemically fractionate and form different minerals that will have variable aluminum to magnesium ratio. For example, olivine doesn't have much aluminum, so it will fall somewhere here, whereas plagioclase doesn't have much magnesium, and that will fall somewhere here. So this chemical fractionation basically starts the clock where 26 aluminum starts decaying. As time passes, the 26 aluminum decays and increases the 26 to 24 ratio proportional to how much aluminum is essentially present in it. And once the aluminum completely decays, this linear correlation is frozen in time, and you can use, and that is called as an isochron. So after a complete decade, this isochron, or the linear correlation, is preserved in these meteorites and these or other objects like quantity components like CAIs and conroos. So you can use the slope of this line and then compare it with another object and calculate the time difference. And that's how you use short-lived radionuclides as relative chronometers. So there are several short-lived radionuclides that have been seen or detected in early solar system materials. And here is a huge list of them. And today we are going to focus on 92 niobium. So different short-lived chronometers have different purposes or different kinds of processes that we can use to date them. So here is a plot that shows the half-life of these short-lived radiochronometers. So, or the usefulness of these short-lived radiochronometers, which is about 5 to 6 half-lives. So the reason I say that is that's when we can actually correctly precisely detect the radioactive decay and calculate the isochrons. So for example, 26 aluminum has a half-life of 0.7 million years. So it's very effective to date events in the early solar system for up to 5 to 6 million years. Similarly, 53 manganese, 53 chromium system has a half-life of about 3.7 million years. So it can date events up to first 20 million years, and so on. Now, the chemical behavior of these elements, the parent and the daughter elements, is also really important. And the fractionation, the reason because of which they fractionate, can actually help you to figure out what process exactly are you dating? So for example, aluminum magnesium differentiation can happen during silicate differentiation or magmatic crystallization. So it's really effective to date those kind of events, and also condensation. Whereas 53 manganese, 53 chromium is very effective for dating secondary processes, aqueous processes in the early solar system. The hafnium tungsten system is really good for dating core formation or silicate and metal differentiation. And niobium and zirconium system is, both of them are refractory lithophile elements. Therefore, they're very useful in dating events like magmatic crystallization, silicate differentiation. And in some cases, when the redox conditions are really low, or the pressure or under high pressure in like bigger planets, niobium can act as a siderophile element, and there you can technically you can potentially use it to date core formation events. So the thing that stands out here about 92 niobium and 92 zirconium system is that its half-life is 34.7 million years, so it can date events up to first 200 million years. So that's very exciting. That allows you to date some really unique things that you cannot date using these other chronometers. So, but there are already so many chronometers. So why do you really need another chronometer or another system? All these systems are very complex. Sometimes they are discordant. So interpreting them is actually very complicated. So I would like to suggest this paper about statistical chronometry of meteorites, which summarizes all the issues related to all the chronometers and a path forward for using these correctly. So for 92 niobium, here I have different early solar system processes that could potentially be dated using these different chronometers. And 92 niobium, 92 zirconium having a half-life of 34.7 million years is actually really useful for dating events on larger bodies like uh, differentiation in the lunar or the mantle, Martian kind of environments. So that's why it's actually a very exciting system. But before we can use this 92 niobium, 92 zirconium as a short-lived chronometers, we have to consider certain assumptions. So the two very important assumptions, since these are short-lived chronometers and all you're dating is the relative time difference, the homogeneous distribution of the parent nuclide, in this case 92 niobium, is absolutely essential, because if you don't have that, then all the different slopes that you get with different materials are basically not going to mean much or not going to have any chronological importance. And the second must have or important assumption, specifically when you're dating or where you're making bulk isochrons, is the homogeneity of the daughter product as well. So wherever in case of bulk isochrons, you make an assumption of an intercept, a common intercept, and then calculate or make an isochron, model isochron. So if you have variations in the x-axis, in the y-axis intercept here, that's going to not really help you with the chronological information out of it. There are certain other factors that can be considered for short-lived chronometers. The first one is how precisely can you measure these isotopes? What is the half-life for the time resolution? For example, aluminum magnesium has a really short half-life of 0.7 million years. So it's useful for up to 5 million years, but the time resolution that you can get is up to few tens of thousand years, depending on the spread on your x-axis. So that's actually very useful and really high time resolution. The third thing that one should consider while using or applying these short-lived chronometers is what are the processes that can be dated? Meaning, what is the geochemical behavior of the parent and the daughter element that fractionates them and starts the clock? So basically, what process are you dating? And the last one is how well do we know the half-life of this? There are certain elements, radioactive elements, where there are uncertainties associated with the half-life, which makes it really complicated to use them as chronometers. So the goal of my work over here that I'm going to present today is to test how homogeneously 92 niobium has been distributed in the early solar system, and if we can use it as a chronometer, and if it is not homogeneously distributed, what does that tell you about the origin and the evolution of the early solar system? So here I have summarized all the previous literature data. So on the y-axis, you have initial 92 niobium to 93 niobium ratio at the beginning of the solar system, as it has been determined using different materials and different techniques as well. So here you can see this is again log scale, and the purple basically shows use of thermal ionization mass spectrometry. This was a very initial, way of measuring isotopes. One of the real big complications for this thermal ionization mass spectrometry technique is that the filament that you use to deposit your separated zirconium after its chemistry is made of ruthenium. It can have contamination for ruthenium, which is a serious interference for measuring isotopic composition of zirconium. So all the green data points over here are the MCICPMS, multi-collector inductively coupled plasma mass spectrometry, and that has been standard way of measuring zirconium isotopes in the recent times here. And this orange one is actually laser ablation ICP-MS. So that's a really interesting one study that measured zirconium isotopic composition in various zircons. So as you can see, there is a lot of variation in the essential, the initial ratio that has been determined, especially these three different studies from early 2000s stand out. So that's really interesting. A lot of these early studies were made on meteorites like mesosideриtes, which are brecciated, and also iron meteorites that can have prolonged thermal histories that could reset different chronometers in different ways. So here is one example of such study, the Sanlup et al. This should be 2001. There is a mistake here. But what they did here is they analyzed one CAI from Iron meteorite for its zirconium isotopic composition, and they assumed a subchondritic niobium to zirconium ratio. So this is not actually measured. And then calculated, and we also know the isotopic and elemental composition for chondrite, bulk chondrites. So this is their model isochron suggesting a really high initial isotopic ratio of 10 raised to 10 negative 3. So, but apart from the early studies here, most of the more recent studies show an initial ratio of 10 raised to negative 5. A lot of this work was initially done by Maria Schonbachler at ETH Zurich, which showed 10 raised to negative 5 as an initial ratio for many of these meteorites. And then as more and more studies were done, people realized that actually selecting the correct kind of rock for these kind of work is really important. We do anchor it with an absolute chronometer like lead. So it is really important to have the kind of rock that has not undergone thermal processing in a prolonged or has had prolonged thermal history, is not brecciated. So all the chronometers that you analyze here are basically concordant or dating a single event. So a lot of work has been done since then, and analyzing certain rocks that are concordant with most isotopic systems, also showing textural evidence for not having complicated thermal history, also suggest an early, the initial niobium ratio of 1.5 into 10 raised to negative 5. And more recently, in 2021, as MCICPMS mass spectrometry techniques get better and better and give us higher and higher resolution, this study analyzed specific zircons and rutils from mesosideриtes. And I know mesosideриtes have had this tortured thermal history, but this study was specifically very careful because they analyzed lead isotopic system, which is the long-lived chronometer, and niobium zirconium system in the same materials. So it's very concordant and not really studying different components. So it's a very careful study that defined the initial solar system 92 niobium to 93 niobium ratio as 1.5 into 10 raised to negative 5, or 1.6 into 10 raised to negative 5 with an error of 0.1 into 10 raised to negative 5. So this is very cool. We know very precise initial isotopic composition or initial 92 niobium to 93 niobium ratio. So now we can use it as a chronometer, right? But there is a twist to the story. So as we know, when you're looking at the stable isotopic composition of early solar system materials, there is a distinct isotopic dichotomy. that classifies these materials into CC and NC reservoirs. So here is the classic Warren diagram with oxygen and chromium isotopes. And here is an example of another system, 96 zirconium, which is a stable isotope of zirconium with no radioactive decay component to it. So that also shows very distinct dichotomy, maybe some variation within the two groups as well, but two distinct groups over here too. So now what if we compare this with the radioactive system? So very recently, last year or year and a half ago, this new study reported niobium and zirconium systematics in a CC meteorite. So NWA 6704 is a carbonaceous chondrite, is a carbonaceous achondrite. It's a differentiated rock, but isotopic composition of this meteorite suggests that it formed in the carbonaceous reservoir. All the previous work that has been done here was on NC kind of meteorites. So all of them defined a lower ratio of 1.6 into 10 raised to negative 5, where this one NWS 67 defines a higher ratio of 2.9 into 10 raised to negative 5. So I should have explained both these plots before I discuss the interpretations. Here you have the 92 niobium to 93 niobium ratio that has been measured in these rocks as they crystallized. And on the x-axis, you have their absolute uranium lead ages. So that basically where it intercepts at CI formation is the initial ratio that has been defined for these different rocks. So here is your NWS 6704, and here are those mesosideриtes that were measured very precisely. So this red line is basically anchored to this data point. And most of the other studies have a little bit higher error bars because they were done a few years ago. So as analytical techniques get better, we can get a really high precision data on these isotopic systems. So on this axis, on this figure over here is basically the back calculated 92 to 93 niobium ratio at the beginning of the solar system. So here is the NWA 6704, and these are all the NC-like achondritic meteorites, and here are the mesosideриtes that were measured by Haba et al. Now, what this suggests is there are distinct two different reservoirs, just like what we see in the stable isotopic R and S process materials. You see that here in 92 niobium and 92 zirconium systematics as well. So the goal of this study is basically to analyze more rocks and see if we still see this kind of difference. So for this work, we looked at Erchesh 002, which is an NC achondritic meteorite, and NWS 6704, which is a CC achondritic meteorite. All right. So Erchesh 002 is a NC reservoir, is a unbrecciated, ungrouped achondritic meteorite with andesitic composition. So this is the oldest volcanic rock in our solar system that we have dated so far. Maybe there are more coming up as we discover more meteorites. Mineralogically, this contains megacrests of pyroxenes that you can see over here, and a ground mass of lots of pyroxene, orgite, pigeonite, and then sodium plagioclase, and a lot of accessory phases like titanium chromite, ilmenite, rhyolite, merilite, and some metal associated with it, and some silica. This meteorite has been dated by different labs for different chronometers. I'm using this one age over here, which is 4565.56. There are some discrepancies in the reported ages for this lead system as well. And then when you look at the stable isotopic composition of these meteorites, oxygen, chromium, calcium, zirconium that I'll show later, all of them suggest that this meteorite formed in the NC reservoir. The second one is NWA 6704, which is again another unbrecciated, ungrouped achondritic meteorites. This is one of the major reasons why we chose these meteorites, is having them unbrecciated and having a very precise thermal history, well-known thermal history is really important in interpreting these data. Texturally, it contains medium to coarse grain cumulate textures with low calcium pyroxene, olivine, plagioclase, chromite, merilite, metals, and metal sulfide. So the phase that basically gives you the higher excess or fractionation in niobium zirconium ratio for this meteorite is chromite. And this is the age over here based on its chromium, titanium, and oxygen isotopes. This meteorite formed in the CC reservoir. And this meteorite, as I showed you earlier, has been analyzed for niobium zirconium system, suggesting the initial solar system ratio of 2.7 into 10 raised to negative 5. So we analyzed both these meteorites, and here are our results. So this is the isochron for NWS6704 at the time of its crystallization that defines an initial ratio of 2.8 into 10 raised to negative 5. And here is the isochron for Urchech, which defines the ratio at the time of its crystallization to be 2.05 into 10 raised to negative 5. So let's go back to this plot that shows the niobium zirconium ratio and y-axis at the time of the crystallization and the absolute lead ages for all these meteorites. So here are the mesosiderite data from Haba et al. That shows really precise early solar system ratio of 1.6 into 10 raised to negative 5, and that basically defines the NC reservoir. Then we look at the other NC meteorites. There are few that have been analyzed. The error bars are slightly larger, but they show a spread along this NC reservoir. And then we have NWS 6704 that defines a higher, almost twice the amount of initial 92 to 93 ratio. And the error bars around it define the CC reservoir. And when you look at Urchech, that's where it falls. It falls somewhere in between, even though it has stable isotopic signatures of NC reservoir. So let's think about this first. What do these higher ratios actually mean when you're thinking about the processing of 92 niobium in the stellar environments? So the sources of 92 niobium are a little bit less understood, not very well understood. It's a p-process nucleosynthetic element, which is proton capture process. And we don't really understand this very well astrophysically. For the longest time, we thought that p-process 92 niobium forms in type 2 kind of supernovae, and then it is delivered into the early solar system. The frequency of these supernovae is about one supernova every 65 years in the Milky Way galaxy. However, more recently, but even the initial ratio of 1.6 into 10 raised to negative 5 is a little too high to completely contribute to the type 2 supernova if you assume like a galactic chemical evolution or an average supernova event. So more recently, Lugaro et al. Did these calculations and also suggested that maybe there is another source, which is type 1e supernova, that also contributes to the initial inventory of 92 niobium. And this kind of supernova is about once every 500 years in our Milky Way galaxy. And now that we know the solar system initial is higher, which is 3 into 10 raised to negative 5, you definitely need contributions from both these sources to explain the amount of 92 niobium that we see in the early solar system. So that's how it forms, and that's what the higher ratio means. What does the heterogeneity mean? So here I am going to compare this with the isotopic dichotomy that has been observed in the early solar system. So, but I do have to mention here that the isotopic dichotomy that you see in the stable isotopic systems is different than 92 niobium, because the nucleosynthetic processes that create the S process or the R process nucleosynthetic stable isotopes, they're basically slow and rapid neutron capture. So different nucleosynthetic process that creates them, and 92 niobium is a P process radionuclide. So the processes that create them and probably the pre-solar carrier phases that delivered them to our solar system are distinct. So there is no reason to assume that these isotopic anomalies should correlate, or you should see NC and CC dichotomy in 92 niobium distribution as well. But since we have seen this dichotomy and spent a lot of time thinking about what could be the causes, we could potentially apply a similar kind of explanation for 92 niobium. So how do we describe the isotopic dichotomy that we see in the early solar system? One of the ways to explain this is heterogeneous composition of molecular cloud material that has been delivered as our solar system is forming. So this, and there are several papers, I'm just using one over here. There are various isotopic systems that have been studied for isotopic dichotomy, and there are various different explanations for it. So over here, this paper specifically analyzed nickel isotopic composition and suggested nickel is more volatile than more traditional refractory elements like molybdenum, titanium, chromium that also show these isotopic anomalies. So what it means is it's not volatility control. That means whatever material came into the solar system was probably heterogeneous in its composition. So what it shows is that were more refractory or more volatile, that they were selectively destroyed with the heliocentric distance and causing this isotopic variations. Or maybe there was some sort of size sorting of these anomaly carriers that created this two different reservoirs. So another interesting thing to consider when we are thinking about these isotopic anomalies and the isotopic dichotomy is whether these variations are temporal or they're spatial or if they are both. So one of the really interesting observation that has been seen by multiple authors, I'm using Jan's paper here for zirconium isotopes, is that you can essentially explain the CC isotopic composition if you start with an NC composition and then add CAI-like component to it. So here is a zirconium isotopic system where you have 96 zirconium, which is a stable isotope of zirconium, and then amount of zirconium. And then you can form these mixing lines, and most of these CC meteorites actually fall on that mixing line. And here are correlations with other isotopic systems as well. So here, for example, is 48 calcium to 96 zirconium. Here are all your NC meteorites. Here are the CC meteorites, and this is where CI is formed. So basically, if you add CI-like component to these NC reservoirs, you can potentially explain the formation of the CC reservoir here. And this is something that has been observed in multiple isotopic systems. So maybe this is something that we can use to explain the 92 niobium distribution here. So this is where your CC reservoir is, this is where NC reservoir is, and there is something weird going on with Archers here, but if you see that, maybe there is a CI component that has been added to the CC reservoir that could potentially explain this. But there is a problem here. Analyzing 92 niobium and 92 zirconium system in calcium aluminum rich inclusions is very challenging because both of them are refractory lithophiles that most of these CAIs show a single 92 niobium to 90 zirconium ratio and therefore don't really define an isochron or show a spread on the x-axis. So here is some data that we collected back in 2016 that we analyzed about more than 15 CAIs for this and only found excess in one CAI. So we got very lucky over there. And this 2-point isochron, which is not really a very good way of defining an isochron. So please take this data with a little bit grain of salt. It defines a lower ratio of 1.6 into 10 raised to negative 5. So we absolutely need to analyze more CAIs for this system to actually confirm that this is the case and there is nothing weird going on with this one CAI and this is not some sort of a mixing line and it's an actual active decay of the radioactive 92 niobium into these CAIs. So now with all those caveats, if we take into consideration the isochron that has been defined by these 4 CAIs, which which shows initial ratio of 1.6 into 10 raised to negative 5. Now these CIs have not been dated using lead system, but let's assume CI formation age, and this is where the CI data falls. So that's confusing. So basically adding CI-like component to the CC reservoir cannot really explain why this is elevated compared to NC reservoir, which is something that has been used to explain the stable isotopic NC-CC dichotomy. So what are other options? So let's think about spatial versus temporal heterogeneity. As you can see, NWA 67 and EC 002 are early formed achondritic meteorites that show variable amount compared to later formed meteorites as well. So there is no, and then you have CIs that also form early but show lower amount of initial 92 niobium to 92 zirconium. So there is no clear temporal correlation between the distribution or the initial abundance of 92 niobium here. Similarly, CIs form very close to the sun, and then CC reservoir potentially forms also in the inner solar system, and NC reservoir forms in the outer solar system. So spatial variations are also not a very good way of explaining this kind of heterogeneity. So what's really going on here? So here is a potential explanation. Oh yes, I did want to mention here that there are other short-lived radioactive systems that have been analyzed for some of these meteorites. So even though stable isotopic systems show heterogeneity, we haven't really detected that in the radioactive short-lived radionuclide systems, except maybe Urchech. There is always controversies related to 26 aluminum. So there are several labs that have analyzed 26 aluminum in Urchech, and that suggests that there may be some amount of heterogeneity, but it really depends on what anchor point you use and what data you use. So this is controversial, and it's probably also not very relevant to 92 niobium, as the sources, the nucleosynthetic stellar source, nucleosynthetic processes and the stellar sources that form 26 aluminum versus 92 niobium are distinct. So let's keep this for a while. The other system is 53 manganese. Now, 53 manganese is really exciting because it is also a p-process nucleosynthetic radionuclide, just like 92 niobium. So the stellar sources that form 92 niobium are probably similar to 53 manganese as well. The difference between the two short-lived radionuclides is their half-lives are an order of magnitude different. 92 niobium has a 34.7 million years of half-life, whereas 53 manganese has 3.5 million years of its half-life. So now there is unfortunately only one CC achondrite that has been analyzed, as far as I know, for the manganese chromium system. And then rest of them are CC meteorites, NC meteorites, and most of them show very distinct homogeneity in the initial distribution of 53 manganese. Now there is Urchech. Urchech, there are two different studies. One of them agrees with this initial ratio, and the other one shows slightly elevated ratio. So there is that controversy. In the same meteorite, same rock, you see two different ratios. The way it has been explained is that if you remember the thin section picture of Urchech that I showed, there are some really large pyroxene crystals in it that are probably xenoliths. That is something that formed before the rest of the ground mass. So one of the interpretations for this discrepancy is that the higher ratio is probably from these early formed xenolithic pyroxenes that record some sort of elevated ratio. And if you only consider the ground mass, then you see this lower ratio. So that can be explained without having to invoke the heterogeneity in the distribution of 53 manganese. So 53 manganese is very well, is probably, as far as we know, given the data points that we have, is suggests that it is homogeneously distributed. But I do want to say that not many CC meteorites have been analyzed for short-lived radio systems. So that's something that we as a community really need to do, and analyze more and more CC meteorites for these short-lived radionuclides to figure out what sort of heterogeneities exist in these systems. So 92 niobium, even though forms with a similar nucleosynthetic process, shows this heterogeneity versus 53 manganese does not. So what's going on here? So here is a suggestion that we could use to explain this data is thermal processing of presolar carriers, which is also something that has been suggested for the stable isotopic dichotomy here. So can we test this though? And there is another explanation too, is some sort of size sorting of these thermal, the presolar carriers that could potentially, for some reason, have different distributions in these different meteoritic parent bodies, and could explain this. As far as I know, there is no clear way of testing this size sorting part hypothesis in these early solar system materials, but we could potentially test it, have an independent test for the thermal processing of these carriers. So here is an example of rare earth elemental abundances of Earth-Chech. And for some reason, it shows really high amount of, it shows like very flat pattern, suggesting there hasn't been much volatile loss compared to other achondritic meteorites that show very fractionated patterns. Now, in some cases, rare earth elements like both Earth-Chech and NWS 6704 are desert finds. So it's really easy to contaminate them. So one of the suggestions that actually Doug Middlefield gave me is that considering the sodium content of plagioclase. So now this is an igneous mineral, and there is something that's really weird. Both NWS 6704 and Earth-Chech show really high amount of sodium in the plagioclase, up to like 10 weight percent Na2O. So here on this axis, I have sodium to aluminum bulk ratio. And on the x-axis, I have the initial solar system ratio as defined by these different rocks. And although I have this data plotted here, the error bars are really large. So it doesn't really mean much except the mesosiderite data that defines this line over here. And then you have NWS 67 that has higher sodium content, but also higher amount of 92 niobium and 92 zirconium ratio. And Earth-Chech is somewhere in between, but also suggests higher amount of ratio. Here, there is another meteorite, Estacado. It's showing something interesting, but the error bars are also very large. So it would be really interesting to redo these analysis in this meteorite. I think they were done in early 2000s, and we have much better analytical precision and analytical techniques to repeat and get more precise numbers on this meteorite. So in conclusion, both the meteorites that show higher 92 niobium to 92 to 93 niobium ratio also suggests that their parent bodies were rich in volatile or accreted volatile rich materials compared to the ones that show lower ratios. So here are my conclusions, and then I'm going to stop here. The first one is that 92 niobium, 92 zirconium short-lived system in these two ungrouped achondritic meteorites suggest heterogeneous distribution in 92 niobium. The higher solar system initial for 92 niobium to 93 niobium can be explained by contributions from both type 1a supernova and type 2 supernova with two distinct carrier phases. The 92 niobium carrier phases for both of these were homogeneously distributed. However, type 1a supernova carrier phases were probably relatively volatile and selectively thermally processed in the protoplanetary disk, giving rise to the heterogeneity in the initial abundance of 92 niobium. The higher solar system initial of 92 niobium still can be explained by type 1a and type 2 supernova if you consider the galactic chemical background levels. And therefore, you don't really require an excessive supernova input at the beginning of the solar system to explain these P process abundances. So I'm going to stop here with that and take questions.
Thank you, Prajkta. Yeah, we will open it up to questions. So if anybody has any questions in the chat, please type away. If anybody here, Carl?
Right, so that was really interesting talk. Congratulations on your conclusion so far. And you mentioned, of course, that you need to have more CC achondrites, for example.
Absolutely.
And so, have you thought about doing NWA 011? That's a eucrite-like basalt. That would be a very interesting one. And there's also a pair of that. There's a pairing of that. In case you can't get NWA 011, there's an identical one that was found that is the same meteorite, but it's just a different NWA number. And also, there are also quite a few of these interesting evolved achondrites other than Earth-Chech, right? So there's there's a whole, there's like a half a dozen of those. I'm not saying that that's easy to get uranium lead ages on, right? But it would be really cool if you could fill in some of the blanks on that. Maybe something out of that would emerge.
Absolutely, absolutely. We do have plans to analyze more achondritic meteorites and also iron meteorites. The criteria that we have for selecting our meteorites is how well do we know their thermal history and how well they have been dated using other chronometers, because that kind of introduces other uncertainties. So absolutely, like we are thinking about doing more meteorites over here for this isotopic system and more CAIs too.
Well, thank you, Carl. Any other questions?
Well, I have another question then, why not? So, for the devil's advocate, what if you just got rid of the CC line and the NC lines on your best fits? Because after all, the CC line is only constrained by one data point, you know? And just say like, well, maybe it's just really fuzzy, especially with those really old ones, right? And actually you can draw a single line through everything. I know a lot of those data points have gigantic error bars. But you know, as you get to the older and older ones, they sort of are clustering there. You know, you have Erdchach and you have 6704, I think it is. And so those are really actually pretty close to each other, you know, and they're also the best measured. So one could argue like, well,
Absolutely.
maybe back there between those two is actually the real value for everything.
Yeah, absolutely. I don't think it's a distinct CC-NC distribution like you see for the stable isotopic anomalies. And here, if you look at this plot, the only three data points that are very precisely measured are these mesosideриtes that are defining the NC reservoir. Everything else has really large error bars. Then for CC reservoirs, the NWS 6704 and the Erdchach. Everything else, the error bars are significantly larger. So we absolutely need more meteorites and more data points on this plot to understand how, whether it is truly NC or CC, or whether it's just a random heterogeneous distribution, and what does that mean?
Thank you, Carl, again. Anyone else with any questions?
Yes, may I, if I can?
Yes.
Yeah, go ahead.
Hi,
This,
Chingsu.
hello. I want to clarify to one of the comments that Carl made. The blue line there on this graph for NWA 6704 is not a line passing through a single data point. The slope here is actually dictated by the decay constant. So
Yes.
okay,
Yes.
so it doesn't matter as long as it is away from another different line. It is on this graph. It is heterogeneous niobium. That's just a physical point.
That's true.
Yeah.
That's true. We have used these meteorites, like for NC, the mesosiderite number, and for CC, the NWA 6704 number. And then these lines are not just random, but they're actually the decay, using the decay constants, they're decay lines. And that's how you define the initial composition. That's right.
Exactly. So, but that said, of course, we want to have more CC-like material to
Absolutely.
verify a singular observation. But that said, I also have a comment to your earlier remark or critique on the Christiania of aluminum 26 plot of similar nature.
Mhm.
Because this one, you said this is controversial because some of the things are dependent on anchor point and whatnot. It is not, because this is everything. I mean, the audience should be realized every single data points or x point, or y point are independent isochron. It is direct observational data plotted. There is no anchor. It is absolute age of lead age for that particular data points, and then the slope from aluminum 26. So every data point made of two observational isochron that is plotted. So sheer simple observational data plotted together, and once, as long as you can defend the data is accurate, then the heterogeneity is shown.
Absolutely. I think Earthshare 002 does show heterogeneity when you're talking about 26 aluminum, 26 magnesium system. The point the 2 points that I wanted to make here is that it is not a simple NCCC dichotomy as you see in the um, um, stable isotopic systems. And secondly, even though this is true, that probably does not directly correlate with 92 niobium system because the nucleosynthetic processes that form 26 aluminum are different than 92 niobium. So just because you see heterogeneity here or homogeneity here doesn't directly translate that you should see something in 92 niobium, 92 zirconium system as well.
Yeah, no, I'm not disagreeing with that part of the statement. When you said this one is controversial because of the anchoring issue, there is no anchoring issue. That's what I'm trying to clarify here to the rest of
Okay.
audience.
Thank you, Shinzu. Does anyone else have any final questions or comments?
That's it, yeah.
All right, well then, thank you, everybody. Prajkta, once again, thank you.
Thank you for inviting me.
Yes, great to have you with us. Real quick, two announcements regarding next week. Since most of the people will be at LPSC, we will not have a Planetary Science Seminar Series next week. So please, everyone, have safe travels for next week to LPSC. And then the following week here in New Mexico, it is our spring break, so we will not have a Planetary Sample Science Seminar Series again. So we will see you guys in 2 weeks' time frame, or no, 3 weeks' time. Yeah, 3 weeks' time frame. For the next one, which will be Carl Vivitz from Johns Hopkins and APL. And we're talking about cryogenic lunar samples and analysis capabilities with that. So once again, everyone have safe travels to LPSC for those that are going, and we will see everyone in 3 weeks' time. Thank you.